So I thought I would start with the fable, which is the topic of this talk, and I'll just read it out loud. A lion lay asleep in the forest, his great head resting on his paws. A timid little mouse came upon him unexpectedly, and in her fright and haste to get away, ran across the lion's nose. Roused from his nap, the lion laid his huge paw angrily on the tiny creature to kill her. "Spare me," begged the poor mouse. "Please let me go, and someday I will surely repay you." The lion was much amused to think that a mouse could ever help him, but he was generous and finally let the mouse go. Some days later, while stalking his prey in the forest, the lion was caught in the toils of a hunter's net. Unable to free himself, he filled the forest with his angry roaring. The mouse knew the voice and quickly found the lion struggling in the net. Running to one of the great ropes that bound him, she gnawed him until it parted, and soon the lion was free. "You laughed when I said I would repay you," said the mouse. "Now you see that even a mouse can help a lion." So this is a fable that has endured over many years in its popularity, and it's certainly popular with children, popular with my children who are here tonight, because it shows that that even very small, powerless seeming creatures can have an effect in the world at large and can matter to things that are really much larger in scale than they are themselves. And so what I'm going to try to convince you are this evening that some of the things which are the very smallest motions in the ocean, things that are the size of this room, things of the size of this podium, matter to the large-scale circulation and the large-scale climate. But to start with, I'm going to show you, we're going to start at the large scale, start at the big picture things, which are the way people originally looked at the ocean. And so one of the things people did when they first started going to make measurements of the ocean was they would go out in a boat and lower something that was able to measure temperature down to the bottom, bring it up, move the ship, lower it again, and you can make a map of what temperature looked like along a particular track throughout the ocean. And it looks something like this. So on the left here, this is a map of what temperature looks like. And the track of the ship here is this little line here all the way down the Atlantic. And you can see the color, and both the color and these numbers represent temperature that gets colder as you go from top to bottom. And this is going from north on the right to the very southern end on the left. And so people first started making these maps, and they could see general patterns of distribution. They could see it was colder on the bottom because cold water is denser than the warm water on the surface. And then if you look at them, you can start to see suggestions of the way currents are moving around the ocean. And in particular, you can see things like here, you could see water that looks cold and dense, which is spilling out of the Southern Ocean. This is very cold, dense water that's formed around Antarctica, and it spills out to the bottom of the ocean great distances. You can make similar maps of salinity, which is what's shown on the right here for the same section. And you can see other types of suggested patterns that you can see there's more sort of saltier, colder water that's formed in the North Atlantic, and it kind of spills out, and you can see this nose of it kind of propagating along this way. So people started making these sorts of maps and got the idea that the circulation in the ocean was large scale, was slow, was smooth. And then people started making more and more measurements in the ocean, and they kind of filled out the picture, and the more they looked, the more complicated the picture got. So this is all the tracks of the World Ocean Circulation Experiment, which made those types of measurements, moving a boat, dropping something down to measure temperature, getting up, moving the boat again. All of these lines all over the world over decades of work, and this program or its successor is still ongoing today. And what you get from this is a map of what this large-scale circulation looks like in the ocean. And this is alternately called the thermohaline circulation or the conveyor belt or something along those lines. And people draw these kind of crazy spaghetti diagrams like this. This is from my colleague Lynn Talley, who's here at Scripps. And you can see water that's getting dense and cold and sinking some places, coming up in other places. And it's this complicated pattern throughout the globe. But then it gets worse, because the closer you look, the more complicated it gets. And so I'm going to show a plot now that's looking from the bottom up at the Southern Ocean. There's this large-scale current at the Southern Ocean called the Antarctic Circumpolar Current, which just goes round and round and round. And so initially, the way people measured it and simulated it with computer models looked like this. So this is, now we're looking from below. Here's Antarctica, and the color here is the speed of a current. And this is this Antarctic Circumpolar Current, which is going round and round and round. And so you think, okay, that's fine. It's a smooth, large current that goes round and round. But if you look more carefully, either by making observations at smaller scales or running a computer simulation with smaller scales, all of a sudden it does not look smooth at all. It looks like this. And suddenly the ocean is filled with eddies. It's filled with swirly, wiggly currents that are much smaller scale than we've seen before. And if you average this for a long time, it ends up looking like the one on the left, that if you average it, if you smooth that out in space and average it in time, you get something that looks like the smooth round and round current, but that's not what it looks like at any particular time. And it turns out that if you look even smaller scale than this, it just gets more and more complicated. It's like a fractal. The smaller you look, the more complicated, the more nonlinear, the more swirly it gets. So the motivation for a lot of my work and the work in our group is that the ocean, far from being large-scale, lumbering, slow circulation, is actually filled with a lovely confusion, this is Walter Monk's phrase, of swirly, turbulent, rapidly evolving things on a variety of scales. And furthermore, that these are not just curiosities, but the details of these small-scale, swirly, turbulent patterns matter for the large-scale circulation and for the climate. And so I'm going to try to convince you of that today by describing a series of 3 kind of vignettes of work that are going on in our group. These are 3 different types of examples of the things we are working on that each show a different example of how small-scale processes, small motions affect something much bigger. So for the first one, this is a picture that I took on the roof of Nuremberg Hall a couple years ago, and you could see something similar it's a little bit too dark right now, but about 15 minutes ago when I peeked out the window here. What I'm looking at, so this is a Scripps Pier, it's right out there, and I'm looking at these lines, these parallel, can you see those in the audience? These parallel slicks here. Here's one picture, and then here's another one I took about 20 minutes later, and you could see those lines have moved a little bit further inshore. Does anyone know what these are, these lines? You see them all the time here, and really in lots of coastal places. So the speed it takes, the one thing I will tell you they are not the waves that we surf, because those waves come in really quick. They do not come in at this very slow speed, which is the difference between the 2 slides. So to get an idea of what these are, we have to look beneath the surface. So here's some measurements. So there's temperature measurements at the end of the Scripps Pier, and so you can see how temperature at different depths evolves in time from that data. This is from colleague Eric Terrell. And so here's a picture of what that looks like. So what's plotted here is, so this axis is depth, and this is time over a few days, and the color here represents the temperature of the water. So you can see a couple things here. First of all, once again, warmer on top, colder on the bottom. Cold water is denser, so the warm water is on the top. The black line is the height of the sea surface, and you can see that's going up and down with the tide. The tide goes up, tide goes down, the whole water column goes up and down. But what's interesting to me is that if you look at this interface between the warm water on the surface and the cold water below, it's also going up and down, and it's going up and down with a similar period, which is about every 12 hours. So what these are, as was mentioned briefly in the introduction, so analogous to the waves that you see on the surface, these are what we call internal waves. And so these are waves that are not propagating on the surface of the ocean. They're propagating on the interface between warm water and cold water, between light water and dense water. And just like if you imagine a little desk toy that has oil and water, anything of 2 different densities, you can see waves on the interface that are different from the waves you can see on the surface. So a couple of things distinguish these from the waves that you see normally on the surface. So the waves on the surface, what we call the restoring force for those in physics parlance, is just the weight of the water. You pick up water, it falls back down due to its weight. And so then that can propagate away as a disturbance. Here, when you move up this colder water, it is denser than the warm water, and so it also wants to fall back down. But the difference in density between the warmer water and colder water in the ocean is much smaller than the difference in density between water and air, and so it falls down much more slowly. We say the restoring force is lower, and it falls down very gradually. So instead of the waves, good period surfing wave is 10, 15 seconds. These waves have periods of hours or longer. So they're very slowly going up, very slowly going down. And the other thing that means is that they can get really big. They can grow to be waves of unusual size. And so waves at the surface, a few feet. These waves can be up to 100 feet. So there are these large, lumbering, giant undersea waves that you can, and the only part of them that you can see is the convergences and divergences associated with their motion make these slicks. And so that is the surface visible manifestation of these giant waves, which are there in the ocean all the time. I'm going to show you a couple pictures of them. So just a brief aside, they're also there in the atmosphere because the atmosphere also has differences between density at different layers in the atmosphere. And so you see similar things. Here's a couple pictures from above of clouds, and you can see similar types of internal waves propagating on density interfaces in the atmosphere. And whenever you see bands of clouds that aren't, skywriting, there are these types of phenomena. So in the ocean, there are a bunch of different things that make these types of waves in the ocean, but one of the largest ones is the tide. And so that was suggested that by that previous picture that showed that interface at the base of the Scripps Pier rising up and down with the tidal period. And so the way that works is if you have a layered ocean, so you have lighter water above denser water, and the tide sloshes that whole ocean back and forth over a bump or over the edge of the continental shelf or any type of topographic feature, it perturbs that interface. So this whole water here is sloshing back and forth over the bump. So the water has to go up and over, and that perturbs the density line between warm and cold water, and that makes waves on that interface that can propagate away. So far from being just a coastal phenomena, this is something that fills the oceans in general. And here's a plot from a couple of my colleagues. This is actually data from a satellite looking down at the surface of the Pacific in the similar way that we can see slicks out the window here of internal waves propagating up our coast. This is a satellite view of those slicks. And here the red colors are propagating north, and the blue colors are propagating south, and these are waves, internal waves created by the tide sloshing back and forth over the Hawaiian island chain. And so these waves can propagate for thousands of miles across open ocean basins and for smaller distances up on our coasts. So the reason we're interested in them is just like the waves that break at the beach that we surf or swim or boogie board in. When these waves propagate into shallow water, they also break. But unlike a couple, a wave that's a few feet tall breaking, now imagine a wave that's, 20, 50, 100 feet tall that's breaking and overturning the entire water column at times. So when these waves break, when they come up to the coast, they mix up heat, they mix up nutrients, and they mix pollutants. And they're one of the largest drivers that provide nutrients to near the surface, and that mix around various other things in the coastal ocean. So that's why we study them. So one of the places where our group is studying them is just outside the door here in La Jolla Canyon. And so La Jolla Canyon is our backyard. It's known to be a site of very high biological productivity, and one of the reasons we think it's so productive there is because these types of internal waves are funneled into the canyon, and the canyon gets narrower and narrower and narrower, and that makes them break, and that makes them mix up cold, nutrient-rich water up toward the surface that fuels a variety of ecosystem phenomena that fuse that have ramifications all the way up the food chain. So one of the types of measurements that our group is making there to see these types of internal waves is from this instrument here. So this is what's called a wire walker, and is developed by Rob Pinkel, one of my colleagues here at Scripps. So it's powered by surface waves. So it's got a little buoy at the top and this profiling thing. The surface waves move the buoy up and down, and that ratchets this instrument, mechanically ratchets it down the line. When it gets to the bottom, it releases a lever, it's mildly positively buoyant, and it floats up to the surface. So it goes up and down, up and down, up and down, driven only by the power of the waves, which is pretty cool. So there's been one of these in the Scripps Canyon for most of the last year, and these are the types of measurements it makes. So on a long time frame, you can see seasonal changes. The top plot shows us the evolution of temperature as a function of depth on the y-axis over most of this last year. And you could see, again, warmer on top, colder on the bottom. But then it gets there's a seasonal cycle to that temperature change. The next plot is salinity. You can see runoff events as they're pointed out, so various things that happen over the course of the year. And then the final plot, this instrument is also measuring a way to infer the chlorophyll content of the water column. So we can see how the ecosystem responds to these changes of physical forcing and the changes of breaking waves. And if you zoom in, here's just a small period zoomed in on some of this, and you can see these types of internal waves propagating up the canyon. So what did this temperature plot here, it looks like the temperature at the base of the pier. Every time the temperature goes up and down once a tidal cycle, that's an internal wave propagating through. And you can see in the bottom plot that there's this peak in chlorophyllofluorescence that's following the peaks and trough of that internal wave. And in fact, the turbulent mixing associated with that wave is bringing the nutrients which are fueling the plankton growth, which provide for that signal. So these are ongoing measurements made in our backyard to help monitor the health of our coast and to monitor our local environment. So a related experiment that I've been part of, which is hot off the press, is a project funded by the Office of Naval Research. And so there's a whole group of us right now, although not me because I'm here, making measurements up the coast by Santa Barbara. So what's here is, this is a little outcrop is called Point Sal, and it's just a little bit north of Santa Barbara. And so the types of things, and there's quite a variety of people involved with this experiment. I've put the people in bold who are here at Scripps. And there's quite a variety of phenomenon happening at this place, as is often true in the coastal ocean. So you can see some of these same slicks. These are internal waves propagating in, but you can see other things as well in this photograph. You can see as current goes around this point, it breaks off and makes wakes, the way that flow in a stream does around rocks. And you can see hints of rip currents, you can see blooms, you can see red tide. So all of these different types of phenomena are happening at once. So this work was motivated, we began this work by trying to make computer simulations of what we expected in areas like that. So here's a computer simulation from Ata Sawanda, who is a postdoc here at Scripps. So what's shown here, this is a little map. So here, this is a zoom in on that region, Point Sal, just up the coast, and the color here is temperature at the surface, and the little arrows are going to be the direction of the currents. And you can see that it's really very complicated. So there's changes in temperature day and night. There's changes in temperature as wind drives upwelling systems. You can see wakes being created sometimes by the coast. You can see slicks of internal waves moving in. And so all of these things are happening simultaneously, and this whole range of complicated processes is what drive the dispersal of things, is what drives the ecosystem, is what drives the heat content of the coast. So we have a big group that's funded by ONR, which has been spending a lot of time up there the last 2 months to try to understand all of these complicated things which are happening at the same time. And so the way to attack something that is so complicated is to bring everything you have. So we have gone up there with pretty much everything but the kitchen sink. Here's Santa Barbara, and so where we've been working is this stretch of coast right here, right by Pismo Beach. So one of the things we have been doing is putting a bunch of buoys in the water to make longer-term measurements of temperature and salinity and ocean currents. And so we brought quite a few. And so these are the ones that are in the water right now. These represent investments from many different institutions, some from Scripps, some from our colleagues at Oregon State, some from University of Washington. And so we put in well over 150 of these buoys into the water, which is sort of a quite an amazing undertaking. But there's more. So then we also have spent time up there, and there's people up there right now, surveying with different ships. And this has kind of been an experiment that's been unprecedented in scale in my experience, and the number of ships involved. So we have been up there with 3 large research vessels, the Sally Ride and the Sproul from Scripps, the Oceanus from Oregon State, and then 3 smaller boats. The Sally Ann is run by Falk Fedderson's group here at Scripps. And so we've been up there. This is the way these types of experiments go, is you go up there with all these people, and we're on these different ships, passing these Google Maps back and forth every night, saying, okay, well, let's survey around here. Okay, well, if I do the green line, you do the red line. Okay, how about I do the orange line? And making these coordinated surveying attempts to understand something that is incredibly complex, varying rapidly in space and time. And you get things that look like this. So this is a little map of the type of things that we're trying to understand, and these are all the same place. These are a bunch of repeat occupations of one area around Point Sal, which is this little outcrop. And the arrows here are the ocean currents at the surface, and the color is temperature at the top 20 meters of the water column. And these are different times, so each of these took about an hour and a half, and you go back and forth, and you can see where we are here in the tidal cycle, which is this little inset. And so I'll just point out a couple things which give you the flavor of the type of things we're studying. One is that if you look at the tide here, here's the tide rising and falling. So the black line is the tide over several days, which is the same in all plots, and the red little dots are where we are in the tidal cycle. So between this one, and this one, the tide is falling. And in this area, when the tide falls, the ocean goes south. And you can see these currents that are getting stronger and stronger and going further to the south. But then, because they're going around this outcropping headland, it makes this big eddy. You can see this swirly thing in the lee of it, which dies out over a couple periods. So it goes around this piece of topography, and it makes a swirly wake in the background, which is one of the things that's mixing things up, and one of the things that regional forecast models don't have a good appreciation of. You can see, if you look at the temperature pictures, you can see these little red spikes here. These are some of these internal waves. Here's some more over here. These sort of rapid up and down things. So these are the types of internal waves which are happening at the same time. And you can see some areas where it goes rapidly from red to blue. There's some very sharp fronts of different types of water masses coming together. These fronts have a lot of visible foam on them. They often are full of fish. They're full of dolphins because they bring together different water masses that produce mixing, that produce nutrient upwelling, and they're sort of feeding the base of this ecosystem. So this is the type of things that we're studying, and it's incredibly rich and incredibly complicated and quite daunting. One more point I want to make about this particular experiment is the Sproul that was out here right now was a special cruise that was run entirely by students. And so this cruise was led by one of my students, Andre, here in the center, and it was part of the UC Ship Funds program. So this is a very unique, very special program at Scripps, which involves specific funding to pay for student-led projects. So they have an opportunity to go out and try out their own ideas and lead their own fieldwork. And so this is a group of students. There's one postdoc from our group who went, and all the rest are students, some from Scripps, some from our sister institutions in Mexico, and some from other places. And they went out there and were a crucial part of the larger experiment and got to test out some of their own ideas, and it will form part of the thesis work for several of these different students. So this is an incredible program for them and for all of us. And then on that topic, here's a few words, a brief video we made on the importance of education at sea. This video features my colleague John Mickett from the University of Washington from a different expedition that we did together, interviewing several Scripps students.
When you come to sea, you get to learn from the experts, so when we become scientists, we'll know how to do it.
You know, sometimes I can be kind of hard on you guys when we're using these instruments. Like, don't touch that, get back from that sensor. They're really expensive, as you know, and they're custom. So if you kind of improperly use them, right, or are not careful around these instruments while you're working on them, it could really jeopardize our scientific mission, really.
Most of my time is spent working on data analysis, and so it's like a really small time, basically like pre and post cruise, where you get to actually work more hands-on with the instruments.
You have to go step by step, and if you miss a step, if something gets screwed up, the whole system can fail, and you just stop. The science stops.
it's pretty amazing, like just all the complexity that goes into each instrument, designing and building it, and then the care that must be taken when you're deploying them.
Okay, so you have to measure the exact quantity, right? It's very important that you get it just the right amount for this whole operation. And and if the ship's rocking a lot, you might want to help somebody, get somebody to help out with this. If you're looking down on it, it's going to be counterclockwise, and you're going to turn that to lock it in. Temperature is key here. Like too hot, it's going to be really too cold, just not going to produce the same result. It's pretty good. All right, let's get back to work.
Which brings up another point, the importance of retaining your sanity by bringing a very good espresso machine to sea. Okay, so switching gears, I was going to talk about the next sort of example or vignette I have involves some work we've did recently in the Arctic. This is work funded by the National Science Foundation, and the ship here is the Sikuliak, which is operated by the University of Alaska. So, as many of you may have heard, the Arctic is melting. Here's some examples of that. So this plot here, I pulled this from the National Snow and Ice Data Center just a couple days ago. This is a map of sea ice concentration as of, I think, this past Friday. Looking down on the Arctic from above, the orange line here is sort of where it used to be for, hundreds and thousands of years. And you can see where it is now, which is retreated substantially. Almost as important as the retreating of it is the fact that it has gotten very thin. You can see the color here is the concentration of ice. So what used to be thick multi-year ice is increasingly now thinner and thinner first-year ice. The average Arctic sea ice extent is going down steadily. There's, some ups and downs between different years, but if you look at the trend is clear. So one of the things that's confusing, though, about this process to us is that it is actually melting more rapidly than expected. So people run forecast models and simulations that take into account everything we know, including global warming, including circulation, and they predict the rate the ice should be melting. But when you look at these plots, it's melting faster. And so there's some types of positive feedbacks which are not included yet in those models, which must be responsible for the acceleration of the ice melt. So in order to understand that, you need to know something that's kind of funny about the Arctic. So here's the normal ocean. As I've mentioned several times, the normal ocean has warm water on top, which is light. It is less dense. It has cold water on the bottom, which is more dense, and so it's denser, and so it sinks down. The Arctic is a funny place. So the Arctic, on top of the Arctic, has cool water that's cool but fresh. And so because it's fresh, it doesn't have much salt in it. It's from melting ice. There's a very large amount of river runoff in the Arctic. So it floats to the top, even though it's relatively cold, because it's not very salty. Below that, there's often a layer that is warm but salty. So there's this lurking reservoir of heat below the surface, which sits below the surface because it's saltier, and so it's denser. But one of the feedbacks that might be happening if there are increasing ways to mix up this heat that's lurking below the surface, it might be accelerating that rate of ice melt. So the questions that our group is interested in are what physical processes set this structure and what processes might be mixing up some of that heat and possibly accelerating the rate of Arctic ice melt. So to understand that, you have to understand where this warm, salty water comes from, and it turns out to be a confusing but interesting story. So here's a plot. This is Barrow. So this is kind of the northern part of Alaska. And the color here is temperature. So what you see on the lower left portion here is relatively warmer water. This is warmer water that's coming in through Bering Strait, and by relatively warmer, it's 5 or 6 degrees Celsius. So it's not, not so good for swimming, but warm, from the perspective of ice. And then in most of the Arctic, or the portion you see here, this water is near freezing at the surface. So this is that water that's cool but fresh. And so it's at the surface in the Arctic, and it's coming from rivers in different places. And so the question is, what happens to this warmer water coming in the Pacific? Well, some of it kind of gets to Barrow here and turns the corner and kind of goes along as a coastal current, but some of it does not. Some of it subducts beneath the surface because it's denser than this fresh water and becomes these very funny little eddies that we observed. So let me just say, we were driving along. We were in the Arctic a couple years ago for this experiment. We're driving along with the ship, looking at measurements made with this instrument here, which is a kind of a funny looking thing, but it's winched, it gets towed behind the ship, and it goes up and down, and it measures temperature and salinity and ocean currents. And we were driving along, and we were looking at the data come in real time, and we saw this incredibly hot subsurface feature, and we said, what on earth was that? Turn the ship. And so we turned the ship. So we were driving along. We said, what on earth was that? We turned the ship, go back for another look, and mapped out this feature here. So what you can see here, so this is what's colored here is temperature. And so you can see on the very surface here is that cold, fresh layer on the very surface. But below that, there's this little spinning top of really hot 6-degree water that subducted here and went in this little, what we call it, a little hot blob eddy, and it's spinning round and round and round, and it's carrying a little heat bomb that's moving further and further into the Arctic. And so we think there's actually a bunch of these coming off Point Barrow here, spinning off, going down, and carrying these heat in these little heat bombs potentially fairly far into the Arctic under the ice. And so the questions that we're interested in are, to what extent could that heat be mixing up towards the surface? And so here again, this is just now one slice in depth and distance in kilometers. So this whole thing is about 10, 12 kilometers wide and about 20 meters tall, which is small for the ocean. Here it is, you can see the temperature. It goes up to 6 degrees in the middle, and the rest of the water is 0 or -1. So seawater, because it has salt, freezes at a temperature less than, freshwater freezes less than 0. Very warm water. And what's shown on the right is actually is our measurement of the turbulent mixing rate. And so to explain that, here's a picture of one of the instruments in our group. And so what this instrument does, it's again kind of a funny looking sort of torpedo-y thing. It's on this line. This blue line is a fiber optic cable that connects it to the ship. And what it has at the very end are essentially little record player needles. It's a phonograph needle. And so this is something I try to explain to my students in classes I teach, and they're like, what? What is that? I think I read about that in a history book. So it's essentially the same thing, that it's on a record player, and it's a little needle, and it's what we call a piezoelectric crystal, which just means that if it bends, if it experiences a change in pressure, it sends a voltage up, and it sends a voltage up the line. So we have a couple of these on the bottom of this instrument, and what happens is that it falls through the water, and it's falling through water that's just kind of quiescent, and it's just hanging out, and then it gets to some area where there's some turbulent event. And so imagine, what it looks like when waves break at the beach, but imagine that happening beneath the surface of the water. So when it falls through some turbulent event like that, this little very sensitive sensor starts wiggling back and forth, and that sends a voltage signal up the wire, and we record that. And the degree of wiggliness of that signal tells us how strong the turbulence is. And so we can make maps of that, and they look like this. And I should add, it was listed in the previous slide, but this is all the work of one of our graduate students, Effie Fine, and she's working on this for her PhD thesis here at Scripps. And what this is, so the color here represents the strength of turbulence, and this black line sort of defines the edges of this little hot blob of eddy. The color here is a log scale. It's like a Richter scale, so it goes up by factors of 10. And so at the top of this eddy, where there's warm water going into cold, there's a lot of strong turbulence. It's enhanced there. And so what we're seeing this hot water be mixed up towards the surface. And so one of the things we think is producing that is actually the same types of internal waves we could see at the beach. We could see, in the previous plots, these waves on density interfaces here. We think there are waves riding on that density interface, getting stuck, and breaking into turbulent motions, which are then mixing up that little hot blob of heat potentially towards the surface. So the questions we're trying to ask are, how far do these little eddies go? How far do they transport heat in the Arctic? And what rate is that heat being mixed up? And in particular, we know that the heat content of the water coming in through Bering Strait is increasing in our changing climate. So Rebecca Woodgate and her colleagues at the University of Washington have been measuring that for years, and they can see the strength, the amount of heat coming in is increasing. What we don't know, and what we hope some of the work, the analysis we're doing of this project will help us understand, is what happens to that heat. Does it subduct beneath the surface like that, and might it go all the way under the ice and then mix up and accelerate the ice melt? We're not sure, but those are the types of things we're trying to understand. And then finally, before I leave this topic and go on to the final vignette, I just wanted to make a general comment about the Arctic, which is that it is truly one of the most amazing, ethereal, beautiful places I've been, that I have the incredible privilege of working there and getting to see it in the current state. And so I wanted to show you a few images from our experience there. We are heading back next summer if anyone wants to come along. Okay, so final, totally unrelated to that, or at least it would seem so, is work I've been doing in the Bay of Bengal, which is in the Indian Ocean. This is again funded by the Office of Naval Research. It again involves a very wide cast of characters. The red did not show up very well, including all of these people who are at Scripps. So here's a little map. Here's India. Here's the Indian Ocean. So the Bay of Bengal is this area here just to the east of India. So it is notable for a variety of reasons, one of which is the incredible population density associated with this region. So this plot here is a map, global map of population versus longitude. So the longitude, which includes the Bay of Bengal, is some of the highest population density on the planet. More people live inside the circle than live outside of it. So it's an incredibly dense area. And one of the defining characteristics of life in this part of the world is the monsoons. So the monsoons come in the summer, the monsoonal winds, the monsoonal rains, and they often come in an unpredictable manner with these strong cycles of rain and then not rain and then rain and not rain. They produce flooding, they destroy houses, and they destroy many, many lives each year. So one of the things that's very challenging about the monsoons in this part of the world is I said that they're hard to predict. So the basic process of them is actually similar in some respects to hurricanes that we're familiar with in the Atlantic. And as people may know, the hurricanes propagate across warm water before reaching places like Florida or Louisiana, and they draw a lot of their energy from the heat in that surface water, and that fuels them. And so the process by which they go stronger is inherently one that involves interaction between the ocean and the atmosphere. So similar with the monsoons, they come in these waves that move north across the Bay of Bengal. And every time, when I say wave, I mean this sort of wave in the atmosphere of rain, these storm systems that come through. And every time this period of monsoonal rains come through, it drenches the area, often unpredictably. And the reason they're unpredictable is because the rate at which they're drawing heat from the ocean is much more complicated to predict in that region than it is for the hurricanes in the Atlantic. And the reason why it's hard to predict there, and therefore hard to forecast accurately the monsoonal rain so that people can prepare, has to do with the structure of the ocean there. And to see that, you need to think about rain, and we need to think about rivers. So the Bay of Bengal is home to an incredible number of large rivers like the Ganges and the Irrawaddy, which drain their water into the Bay of Bengal. So this little simulation on the left is showing the salinity at the surface, and you can see water coming out of the Ganges, coming out of other rivers, and this water, because it's light river water, it's not salty, it comes out of the rivers and it swirls around and covers in these sort of swirly patterns most of the top of the Bay of Bengal. And so that leads it to be, even though it's very far away, in a strangely similar some strangely similar characteristics to the Arctic, although it is much, much warmer there. So here's the measurements that we made on our recent trip. This is just a long section across the ocean of temperature and salinity. And so this is over about 50 meters in depth, the top 50 meters of the ocean. And you can see that there are these patches when we encounter one of these tendrils of river water swirling around. So the river water has been mixed a bit with the saltier water, so it's not purely fresh, but it's still quite fresh compared to the normal ocean. So like with the Arctic, there are lots of periods where the surface water is very fresh, and so you can get these pockets of warmer heat lurking below the surface because they've been warmed by the sun, but then have been covered up by fresh, cooler water. And so this is why it's very hard to predict the monsoons, to predict the monsoonal interaction there, because the rate at which the atmosphere exchanges heat with the ocean, it gets complicated. It gives heat to the ocean, but the ocean doesn't give it back in a normal way because this puddle of fresh water comes in, covers it, and traps that heat below the surface. So we're trying to understand the processes that stir around this fresh water in order to better predict them, in order to improve the accuracy of forecast models for this region. And so this has been a huge, again, a large international project, and a big component of this project has been working very closely with a lot of Indian scientists. So a lot of the Indian students have come with us, and a lot of our people have gone and worked with the Indians. And so the collaboration fostered by that has been one of the most fun and I think productive things of that project. And so I'll just show you one, one comment is that we're trying to understand the evolution of these little tendrils of fresh water, and many of them are trapped very near to the surface, and so they're hard to see with a normal ship, which tends to churn up the surface water when it goes by. So one of our colleagues has addressed this by developing a fleet of little remote control kayaks. And these are pretty awesome little guys, and they have temperature sensors. They have sensors that measure velocity that are hanging below them for a much larger distance than the size of the kayak. They're gas powered, and they drive around with like a little remote control. So these guys are great. They have little solar panels on the top, and they can drive for 100 kilometers before they run out of gas. And so they can go and make measurements distinct from a ship, and they can go and measure things that are very close to the surface. And they see things like this. This is measurements through one of those little freshwater tongues, and they've given us a kind of unprecedented picture of what they look like. And some of the things that were completely unexpected is that the edges of those freshwater tongues are extremely sharp. We would have expected them to be much more dilute in the open ocean, but the whole change here between freshwater and saltier water occurs over the space of sometimes a meter, the distance between me and the front row, which in the middle of the ocean, 300 miles from the river source, is crazy. And so we think these things are being blown by the wind. Sometimes they're thinner, and so the wind pushes them faster than the other ocean, and so they pile up and make these very sharp edges. So studying how those are created and how they mix away helps us understand the structure, which lets us better predict ultimately the monsoons. Okay, so 3 conclusions to share with you tonight. First is the actual science conclusion, that in each of these examples, there's a small-scale complicated process that's happening that, though it appears small in size, is a building block for something much larger than it, either the coastal systems or Arctic ice loss, or understanding the monsoon. And so the first question is, what can we do to put together these little examples into something that actually improves forecast models? And so one way to do that is by making maps. And so one of our recently graduated students has been making maps. This is a global map of the strength of this type of turbulence in the ocean. And so what she's done is put together a bunch of different types of data. And the color here is, again, a log scale. It's like an earthquake scale. So when you go up one number here, like on the earthquake scale, it goes up by a factor of 10 and then a factor of 100. So there are orders of magnitude, factor of 100 of 1,000 variability in the strength of this type of turbulence around the ocean, but with systematic patterns that are not random. So it's higher in the West Pacific, it's higher along the equator, and so we can map out those patterns and take a physics-based understanding of what drives those patterns, which are things like these internal waves, and turn them into improved models. And so over the last 5 years, I've been leading a national group which is funded by NSF and NOAA, involves lots of different people, and we have been actually taking our composite understanding of some of the types of processes that I've described here today and putting them into climate models to improve the accuracy of our national climate models, our two national climate modeling centers. We've been working closely with them and trying to turn those insights into improved models. And so the accuracy of some facets of them has improved in response. The second meta-conclusion is that a lot of the insights in our field, a lot of the frontiers of seeing new things in the ocean have to do with instrument development. And so some of the instruments I've shown have been from our group at Scripps, some have been from other colleagues at Scripps or other colleagues at other institutions. But innovative new instruments, which are often developed in our field historically at academic institutions like this, have led us to see the ocean in shockingly different ways. So instead of seeing a smooth, large-scale overturning circulation, we see small-scale fronts and waves and turbulence. And so seeing the ocean in a different way lets us understand the processes in a different way. And then the final conclusion is that in most of the examples I described tonight were made on ships. So we are incredibly fortunate here at Scripps to have probably the best fleet in the world of research ships. We have the Sally Ride, the Revell, the Sproul, and the absolutely unique Flipping Flip. And so while there are many other types of ways to observe the ocean now with satellites, with fleets of kind of autonomous robots that swim around the ocean, there's still nothing that beats these old-fashioned types of research trips. So in the examples I've shown, you drive around, you see something unexpected, you say, we have to stop, we have to turn the ship, we have to figure out what's happening here, because there's something confusing and we can figure it out. And so this type of oceanography is important to discovery and important to maintain our excellence in. And that is it. Thanks very much.
Yeah, you showed some pictures of what these internal waves look like from the Scripps Pier. And I just I'm having a hard time understanding how something that's subsurface like that, like, here locally you might get internal waves that are maybe 50 or 100 meters deep, but I know they extend also down to about 1 kilometer. So how are they expressed at the surface? Like, how can they be detected at the surface?
So there are a couple ways. So it's the ones that we see here, the slicks here. So there's as a wave passes by, like, if you sit in a wave and if you're swimming in the ocean, when the wave passes by, you move forward and backward, but you don't move with the wave. The shape of the wave moves, and you just kind of move in a circle. So similarly, when one of these waves passes by, there are convergences and divergences, and where the surface water goes together, even the wave is passing beneath the surface, but they make the water in the upper ocean converge together, which makes all the surface waves and surfactants pile up, and then when they diverge, it makes water kind of upwell, and you get a smooth area. And so that pattern is how you see them. They also turned out, this is actually one of the most amazing calculations I know of, for some of those deep water ones, there's a very slight surface signature associated with them of about 5 centimeters, which is in response to the 50-meter motions below. It's mirrored in the surface to a very gradual extent, which is about 5 centimeters. So using satellites that look at the motions on the ocean surface, if you average out surface waves, large-scale currents, everything, and if you average for years, and if you're very clever, much cleverer than I am with this sort of thing, you can pick out a 5-centimeter signal that's coherent at that frequency propagating across the open ocean. So it's a tricky thing to do, but...
How do these waves impact marine life, if they do?
So there's a couple ways they impact marine life. One, as I mentioned, is when they break, they mix up nutrient-rich water, and so that a lot of animals that live in the euphotic zone, a lot of plankton closer to the surface, depend on that mixing up of nutrient water to get the nutrients they need to grow. But the second way, which is more surprising, is that mostly, as I just said, when you're sitting there with a surface wave and a wave comes by you, you move in a circle, but you don't move with the wave. But you do actually move a little bit, and especially when they get very steep, they move stuff with them. So there's a little bit of stuff that propagates with these slicks that come in. And so there's some evidence that some types of organisms which have different phases of their life cycle, where they have a phase in which they're planktonic and the larvae drift around, and when they're ready to settle down, they swim to the surface or up towards the surface. They get sort of on the train of one of these types of internal waves coming in. They ride that train into the coast, and then they settle down to become, a barnacle or something else that is not swimming, that is sitting on the bottom. And so they can actually catch a ride with some of these, it seems.
So the studies that are being done, the scale models that are being collected, the use for these have what purpose, what effect on any one of us or on oceanographic research in the future? Is it something that could be done or could be used towards prediction of food sources or weather patterns, or even for wave technology as an alternative source of current?
Yes. I'll leave them up. So a lot of the coastal work that I've been doing, that we've been doing, is designed to understand the health of our fisheries. And so a lot of these types of, these swirly, complicated-looking processes that set heat patterns and that set nutrient patterns, those are the things people need to understand and predict in order to accurately to govern our fisheries effectively. And so that's one frequent application to run these models. For example, the stuff in India is explicitly designed to improve our forecast models for monsoonal winds and monsoonal rains, because of the role that the ocean plays in feeding some of those weather patterns in ways that are not very well represented in current forecast models. And then some of the bigger scale global stuff is trying to understand and predict how climate change will play out. And the Arctic is not just sad for the polar bears, but the Arctic is kind of a canary in the coal mine for a lot of the planet, and feeds back through different types of weather patterns and circulation on a lot of the planet. So if we can understand some of these processes improve the accuracy of our forecast climate models, then we can prepare better, if nothing else.